Hi, welcome back to Autonomous Mobile Robots. My name is Davide Scaramuzza and I will be your teacher for this segment. In the previous segment, we have seen an introduction to computer vision, its challenges and applications. Now, let's talk about camera image formation. After starting from one or more light sources, reflecting off of one or more surfaces in the world, and passing through the camera's optics, which is the lenses, light finally reaches the imaging sensor. The goal of this segment is to understand how a digital image is formed. Light falling on an imaging sensor is usually picked up by an active sensing area, which is integrated for the duration of the exposure. The two main sensors used in today's digital cameras are CCD or CMOS sensors, which consist of an array of photoreceptors. If we place this array of photoreceptors in front of an object, do we get a reasonable image? As you can imagine, obviously not, because each photoreceptor is exposed to the light rays coming from every possible direction. In order to see an image, we would like to be able to select a specific light ray for each point in the scene. One solution is to add a barrier with a small aperture, in order to block off most of the rays as it is illustrated in this image. The simple solution is the one behind the pinhole camera or camera obscura, which in Latin means dark room. The pinhole camera has been the first example of camera in the history, which eventually led to the invention of photography. The first published illustration of the camera obscura is from Jim Afrisius, who used this illustration here in his book to describe an eclipse of the sun. A pinhole camera has no lens, but just a single very small aperture. In short, it is a light-proof box with a small hole in one side. Light from the scene passes through this single point and projects an inverted image on the opposite side of the box. The working principle of this camera was already known by the Greek Aristotle and Euclid, and the Chinese Mozi. The pinhole projection model was also used as a drawing aid by artists such as Leonardo da Vinci. As we will see, the importance of the pinhole camera is that its simple principle can be adopted as a standard model for perspective cameras. Now, why do we use a lens in modern cameras? Why isn't the pinhole camera not enough? The reason hides in the inherent limitations of the pinhole camera and in the wave properties of light. If we had an infinitesimally small aperture, we would ultimately allow only one ray of light reach each point of the film. However, the first drawback is that the image would appear very dim. The second drawback is that when the size of the aperture is smaller than or comparable to the wavelength of light, then diffraction effects would occur. Conversely, if we made the aperture bigger, the image would get blurry, as you can understand from this illustration. So the trick consists of using a lens. A lens can focus multiple rays coming from the same point onto a single point on the film. Rays passing through the optical center are not deviated, while all rays parallel to the optical axis converge at the focal point. Let's now try to derive the equations that govern the projection of an object onto the image plane. Let's denote the height of our object with a. We can determine the image of the object by intersecting two rays. We can use as a first ray the one that travels parallel to the optical axis, and as a second ray the one that travels through the optical center. The intersection of these two rays identifies the image of our object. Now, Let's denote the height of the image with b, the distance between the object and the optical center with z, and the distance between the image and the optical center with e. What is the relationship between f, z, and e? To find this relationship, we can use the similarity between these two triangles. From this, we have that b over a equals e over z. Instead, if we now look at these two triangles, we can write that b over a equals e minus f over f, which can be simplified into e over f minus 1. If we now equate these two equations, we get this. And if we divide both terms of this equation by e, we get the thin lens equation, which is 1 over f equal 1 over z plus 1 over e. Now, what happens if z is much larger than the focal length f? In this case, we would just need to adjust the image plane such that objects at infinity are in focus. From the thin lens equation, we can see that when z goes to infinity, then the term 1 over z becomes negligible. From this, we can write that 1 over f equals 1 over e, and therefore that f is approximately equal to e. This approximation is called pinhole approximation. It basically allows us to approximate the lens to a pinhole distant f from the focal plane. So, to recap, using the pinhole approximation, all scene points reproject onto the plane. The center of the lens, here denoted by the letter C, is called optical center or center of projection. With the pinhole approximation, you can notice that these two triangles are similar. And therefore, we can write that h prime over h equals f over z, which implies that h prime is equal to f over z times h. For convenience, the image plane is usually represented in front of the camera, such that the image preserves the same orientation, which means such that the image is not flipped. The image of a point is then found as the intersection of the ray from P to the optical center C. One thing to remember is that the camera does not measure distances but angles, so a camera is a bearing sensor. Now, how do we find the projection P of a scene point capital P onto the camera frame? To do this, we can just use the similar triangles. From similar triangles, we get these equations, as we have demonstrated in the previous slide. And similarly, we get also a similar equation for y. So, until now, we were able to project scene points onto the image frame. Now, we need to convert points on the image frame from metric units, say meters, millimeters, into pixels. In order to do this, we need to account for the pixel coordinates of the camera optical center and the scale factor, k, for the pixel size. As observed from these equations, this can be easily done by first rescaling the camera coordinates by k and then by adding the optical center coordinates u0 and v0. These equations fully describe the projection of a scene point onto the image plane and are called equations of perspective projection. Now, as you can observe, these equations are nonlinear in x, y, and z. To avoid dealing with nonlinear equations, it is very common in computer vision to use homogeneous coordinates. Homogeneous coordinates allow a linear mapping from 3D to 2D by introducing a third coordinate to the image point. P tilde denotes the homogeneous representation of P. Now, using homogeneous coordinates and matrix representations, we can write the two equations of perspective projection into a more compact form, which is this one here. Or alternatively, in this way, where we have replaced the product k times f by the parameter alpha. We call alpha the focal length of the camera in pixels, and k the matrix of intrinsic parameters. The intrinsic parameters are alpha, u0, and v0. Until now, we were implicitly assuming that the scene point P was referenced in the camera frame. But what if P was expressed in a separate frame? Let's denote the separate frame with our world frame. In this case, we need to take into account the rigid body transformation between the world frame and the camera frame, which is described by rotation r and the translation t. The relation between a world reference point and the camera reference point is described by this equation. Using homogeneous coordinates and matrix representations, these equations can be written in a more compact form as this. We can now substitute this expression into the perspective projection equation and obtain the general perspective projection equation, which fully describes the conversion from the world frame onto the image plane. The product k times r and t gives a 3x4 matrix, which is called perspective projection matrix. The aforementioned image projection model assumes that the camera obeys a linear projection model where straight lines in the world result in straight lines in the image. Unfortunately, many wide-angle lenses have noticeable radial distortion, which manifests itself as a visible curvature in the projection of straight lines. An accurate model of the camera should therefore also take into account the radial distortion of the lens, especially for lenses with short focal length, for example, lenses with large field of view. Depending on the type of radial distortion, the coordinates in the observed images are displaced away or towards the image center. These two types of distortion are called barrel distortion or Pynchausen distortion, respectively. The standard model of radial distortion is a transformation from the ideal coordinates, that is undistorted, to the real observed coordinates. The amount of distortion of the coordinates of the observed image is a nonlinear function of their radial distance. For most lenses, a simple quadratic model of distortion produces good results. As you can observe, this model adds a distortion component to the image point, which is proportional to the square of the distance of the point from the image center. This model uses only a single distortion parameter, which is here denoted with K1. This parameter is also an intrinsic parameter, and together with the other intrinsic parameters alpha, u0, and v0, can be determined through a calibration procedure that we will see in the next segment. Thank you for your attention.